This is Unit 11, Lecture C, Alcohols through Organic Acids. Substitute hydrocarbons have one of the hydrogens taken off and some functional group put on. Reference table R is the one we're going to use for this. You should watch the lecture on the reference tables if you are still confused as we go through the lecture. Use this table to figure out which class of compound you have by looking for the functional group. Use it for the example they give you, which will help you figure out the naming rules. We're going to start today with alcohols. That's the first one here. Alcohols all have a hydroxyl group on them, so one oxygen that's attached to a carbon chain, that's what the R is, and a hydrogen. So one oxygen, single bonds attached to a carbon and a hydrogen. If we look at their example, again, this is an expanded molecular formula, CH3, CH2, CH2OH. The OH is attached to the last carbon in the chain, so they're calling this 1-propanol. The number tells you the location of the hydroxyl group. The prop tells you there's 3 carbons total in there. So naming alcohols is pretty straightforward. Count the number of carbons, use the prefix from table P, add ANOL or anol to them. The biggest hint I can give you about that is to make sure your handwriting is neat, because another class of compounds will use the ending ANAL, and there's a slight difference between an A and an O. If the person correcting your test can't read your handwriting, you're not going to get credit. So hydrogens removed, hydroxyl is put on there instead. Notice that they are not bases. That is covalently bonded on to your carbon chain. So the hydroxyl is your functional group. Covalently bonded on, it can't dissociate, it's not a base. General formula R, where the R is your alkane chain, OH. The ending for an alcohol is anol. If I draw out a few examples for you, we're going to do straight chain monohydroxy alcohols. Mono meaning one hydroxyl group. When we're doing their molecular formulas, you could start with the alkane using 1 carbon. So methane would be CH4. Take off one of the hydrogens, replace it with an OH. So you would get CH3OH. And I've drawn the structural formula here. You can also start with the structural formula. So if I were to draw it for ethanol, Eth is 2 carbons. I have to have an OH because it's anol, add hydrogens around. Count up the carbons and hydrogens on the first half of your chain besides the hydroxyl. So there's 2 carbons and 5 hydrogens, and then add the OH at the end. Butanol, the prefix but means 4, so let's draw that one. Sometimes you will see an expanded molecular formula where each link in the carbon chain is written out separately. So I would have CH3, CH2, 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 OH. Different ways of giving the formulas, different styles of writing the formulas out. Be used to seeing all of them. All of these, the hydroxyl is on the first carbon, so really you could write a 1 here, but just like 1 and 1x, it's not necessary. Alcohols get classified into different groups depending on how many hydroxy groups there are, hydroxyl groups. So mono meaning 1, hydroxyl being the OH group. Primary alcohols in our monohydroxy group have the OH on carbon number 1. So 1-butanol, but 4, 1, 2, 3, 4. Number 1, you can put the OH on the first carbon, on the last one. Remember, left, right doesn't matter. In secondary alcohols, the OH group is attached to a carbon somewhere in the middle of the chain, so the carbon is attached to 2 other carbons. These are going to be the ones with numbers, so 2-butanol. Now it's important that you count the carbons. Second carbon in, put your hydroxyl group, and then hydrogens. tertiary alcohols are going to be hydroxyl groups across from a branch. So an example is 2-methyl-2-butanol. So if I start with my 2-butanol, and then the 2-methyl just says on carbon 2 there's also a methyl group, like so, and hydrogens around. It's not important that you know the classifications as primary, secondary, or tertiary. Just be able to follow the naming rules and draw them, and it doesn't matter what we call them, just be able to identify them as alcohols. Two other classes of alcohols, dihydroxy, meaning that there are 2 hydroxyl groups, and trihydroxy, meaning that there are 3 hydroxyl groups, are also ones that you should recognize, but you don't have to know the term dihydroxy alcohol. 1,2-ethane diol is really the only one you need to know here, so let's draw this. Ethane, so eth meaning I have 2 carbons, diol meaning I have 2 hydroxyl groups, and 1 and 2 are locations. So this guy is also called ethylene glycol, and it is the compound that's commonly found in antifreeze. It tastes sweet, unfortunately, but is very poisonous. They make it lots of nice vibrant colors, so we know not to drink it. However, animals will lap it up because it is very sweet. So make sure if you are using antifreeze, you dispose of it properly. If you happen to do your own car repairs and you're draining radiators, make sure the antifreeze goes in a closed container and to a recycling center. Don't let it drip out on the ground. Trihydroxy alcohol that you should know is 1,2,3-propane triol. Prop meaning 3 carbons, tri for 3, all for hydroxyl groups. So 3 carbons, 3 hydroxyl groups on carbons 1, 2, 3. It looks like this. This is also called glycerin, glycerol, or glycerin. We've used it in lab before. It's that really thick liquid. It, in its really food grade form, is used in candies and frostings. In its more industrial form, it's used as a lubricant and a raw material. It happens to be in makeup, happens to be a byproduct of saponification. Way easier to pick out than an oil. So if you see that in an equation when we get to types of reactions, it is probably a saponification reaction. Moving on to the next category on, or another category on reference table R, we have organic acids. Organic acids have a functional group that we call carboxyls, and they have the formula COOH. When you draw the structure of that, it has a double bonded oxygen on the carbon and an hydroxyl group on the same carbon as well. So that's the hydroxyl. So that's our carboxyl group. This arrangement puts stress on this hydrogen-oxygen bond, so what ends up happening is when you put it in a very polar solution like water, you end up ripping that hydrogen off, so you get left behind with this negative portion and hydrogen plus ones, which means these guys are acids. They are covalently bonded because these are all nonmetals, but this stress on that bond is enough to let it snap off and dissociate in solution. The one that really shows up a lot is ethanoic acid. Happens to be on reference table K. So when you're looking for an acid, ethanoic acid is on there. There are others besides that. We name them by using anoic acid for our ending. So methanoic acid, ethanoic acid, propanoic acid. Methanoic acid goes by the common name formic acid. That's the one that insect stings. Ethanoic acid is also acetic acid, and that's the one that's in vinegar. So we'll do a few examples. Coming up with the formulas is usually easier if you draw the structure first. So methanoic acid means I have 1 carbon, and it has to have a double bonded OOH on it. and I just need this other hydrogen to finish off carbon's 4 bonds. When you write the molecular formula, they tend to keep the COOH together, so methanoic acid would just be HCOOH. Let's take a look at the other two. Ethanoic acid has 2 carbons all together, including the one in the carboxyl group, so they typically write this as CH3COOH in organic chemistry, and then pentanoic acid with 5 carbons, including the one in the carboxyl group, so it's going to be C4H9COOH. You might see this flip the other way so that your carboxyl group is coming off the opposite side. Sometimes they'll show you the carboxyl group with showing you the bond between the oxygen and the hydrogen. They mean the exact same thing. That wraps up Lecture C.